Now that we have a precise definition for binary search trees, let's discuss each of the different operations we might want to do. Search, insert, and delete. We'll also do a little bit of runtime analysis as we go. So let's start with search. Turns out the search algorithm is so simple that I'm just going to spoil it because you basically already know it, having done the exercise at the beginning of lecture. How it works is we look at a particular node, t, let's say, and if the search key equals t.key, that is the thing we're looking for, that's the search key, equals t.key, we'll return and say we found it. If, however, the search key is less than t.key, then we'll go left. If the search key is greater than t.key, we'll search the right. And so here, if we look, for example, for elf, we'll look at dog and we'll say, hey dog, are you elf? And he goes, ruff, ruff, no. But we know that elf is bigger than dog, so we go to the right and we get to flat. Okay, well, elf is smaller than flat, so we go left and we find elf and hey, there it is. Now this algorithm also works if, for example, we search for zebra. So if we look for zebra, we'd go right, right, and then we fall off the tree. And in that case, we would just return null. Now you'll notice that my code I've described here does not include the base case because this is just supposed to be kind of the high level picture. And so what the code might look like is something like this. Now this is just pseudocode. This is not real Java, but we might do something like, okay, we have a static method which returns a binary search tree node. So you start with a binary search tree node and you're given a search key, sk, and if the current binary search tree node is null, we'll return null to indicate, hey, it didn't exist. If the search key equals t.key, we'll return t to say, hey, we found it. If the search key is less than t.key, well, then we'll find the result by searching the left, and then we'll return that instead. And lastly, if the search key is actually greater than t.key, well, then we'll find the result on the right, and then return whatever we found. And that could be, for example, null, or it could be the actual answer if it exists in the tree. So hey, there you have it. All right, so it's a beautiful and perfect example of recursion, and it's really just the best way of doing things. Now, when it comes to the lab that you're going to do for binary search trees, you should look back at this code, but you'll be in a different situation where rather than using a naked recursive binary search tree, yours will be clothed. And you'll see what I mean when you get to that. All right, so now that we understand what the search operation looks like, how it works, let's discuss performance. So what I'd like you to do is think about what I will call a bushy binary search tree. Now, bushiness is just an intuitive concept that we haven't defined yet. And your job is to tell me if I have n nodes. So for example, here n is 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. If we want to search for something, what is the worst case search time in terms of n, the number of nodes? And again, I said I haven't defined bushiness, but think of it as a tree that is just as full as you can imagine. A binary search tree, that is as full as you can imagine. So pause the video and think about that. Okay, so it turns out the correct answer here is log n. So we look at 15 items. We only have to go 1, 2, 3 steps in order to find the correct answer, looking at a total of 4 different items. Now to get up to needing, let's say, 6, we would actually need to have about 4 times the amount of tree because at every level, that node, or the number of nodes is double what it was on the previous level. So one way you could think about it is that the height of one of these trees is going to be around log base 2 of n. It won't be exact. This is only true for powers of 2, but the powers of 2 minus 1, that is. The height of the tree, though, will be around log base 2 of n. So here, the height is 3. Okay, great. So, is that good? Well, yeah, it's real good. Turns out that having a data structure where you can find anything in log time is an incredibly powerful and amazing thing. If you have a binary search tree that is in fact bushy, then even if you had a tree that was 10 to the 300,000 different items, which is just a mind-boggling and crazy number, and you had a slow computer that can only do an operation every microsecond, so like, 1 megahertz, that's pretty bad, you would still be able to find something in 1 second, even if it's that big. And What's kind of nice is that, well, most computation time these days is actually, well, arguably, is dedicated towards finding things in response to queries. Like I go to Facebook and I search for something, or I go to Google and I search for something. Or I'm using a spreadsheet in Excel and I want to sort by some number of rows. There's a lot of lookup happening in that process, like finding things. So it's a good thing that we can do search queries almost for free. Now, this is arguable, especially in the modern era of machine learning, where there's quite a lot of computation resources dedicated towards training machine learning algorithms. But I still think it's fair to say that search is a major problem. And so binary search trees excel at it, which is a cause to celebrate. That's the search operation, and we'll see the next two operations in the next two videos.